Hello all. Today we'll discuss about electronic effects. In that, the first one is inductive effect. What is inductive effect? How it operates? And what are the consequences of inductive effect? All these points we'll discuss in this short lecture. When a system or when a molecule is like this, all carbon atoms are there, no other atoms are there. This kind of molecules you can call them as non-polar. There is no polarity in the molecule. So no inductive effect you can say. But for example, if it is given like this, when a chlorine type of atom is attached here, the electrons are attracted towards the chlorine and the chlorine will get partially negative charge. So this will be getting partial positive charge. The electrons are not completely transferred. It is not transferring of electrons. Just because of the more electronegativity, electrons are little bit attracted towards the chlorine atom, so it is getting negative charge. This positive charge present on the carbon atom can be little bit reduced by the carbon atom next attached to this. So this carbon is providing electrons to this one, not by donation, just a support type. The same thing you can observe here, and this can be almost negligible after fourth carbon. Up to fourth carbon, you can expect such kind of electron pushing type of nature, and this kind of effect is called inductive effect. Here, this is all happening because this is a polar molecule. The meaning of polar molecule is one atom is more electronegative, that is having negative charge, partially negative charge. That is because electrons are attracted a little bit towards that one due to more electronegativity. And this kind of charges, when you are mentioning, this is said to be a inductive effect. What are the features of inductive effect? It's a permanent effect. Permanent means because the chlorine atom or the bromine atom or the oxygen atom, what you are saying, this is present in the system, so this effect is going to be permanent. And important thing is, whenever you are saying this effect is there, electrons are little bit pushed like this we are showing, but electrons never leave the atomic orbitals of the atom. They are present always in the same orbital, and this happens only through sigma bonds, not pi bonds. This happens only through sigma bonds, and the polarization will be always in same direction. Means if it is going like this will be going like this only, not this side. Only one direction polarization will be there. And inductive effect generally you can see when there is single bonds, covalent bonds are present, inductive effect will take place. And as the distance is increasing, the tendency will decrease. For example, the inductive effect caused by this carbon will be more and the inductive effect caused by this carbon will be less. As the distance increases, the inductive effect tendency will be decreasing. Based on the nature of attracting electrons, there are two types of inductive effects, plus I and minus I. Basic definition we give like this: if the groups have a tendency to attract less than hydrogen, if they are attracting electrons, they are called plus I groups. If they attract electrons more than hydrogen, they are called minus I groups. The tendency to attract electrons more than hydrogen is minus I group. The tendency to attract less than hydrogen is plus I group. What are the plus I groups? Plus I groups are all alkyl groups you can take. Alkyl groups like methyl, ethyl, all these are the best. For example, tertiary alkyl group if you take, secondary, then primary alkyl group, then methyl type of group, then deuterium, then hydrogen. If you consider, this is the order. This is more plus I group, then this will be less plus I group. When you compare with all this, the plus I nature will be maximum for the tertiary carbon, then secondary carbon, then primary carbon. And if it is given like this, a methyl group, an ethyl group, a N propyl group, and a n-butyl group. Same concept. Here one carbon is there, here two carbons are there, three carbons and four carbons. So this is more plus I group. So highest plus I group, next and last. That means more the number of carbons, more will be the plus I tendency if you are discussing about all primary things. Then minus I group. Minus I group, there is a big order you can take. These we can say electron withdrawing groups. They withdraw the electrons because as we were discussing, they attract electrons more than hydrogen. They are called withdrawing groups. The minus I order I am giving you, NH3 plus or you say NR3 plus. This is maximum than NO2 group, than cyanide group, than SO3H group, than aldehyde, ketone. See the order: NH3 plus, NO2, Cn, SO3H, CHO, CO, COOH, acid chlorides, esters, amides, then halides, fluorine, chlorine, bromine, iodine. Remember these kind of orders: fluorine, chlorine, bromine, iodine, OH, OR, NH2, C6H5, finally hydrogen. So all these are attracting electrons more than hydrogen. The general order you have to remember is fluorine, chlorine, bromine, iodine. These kind of orders you remember more. This is minus I nature. Otherwise, NO2 is stronger than CO group, than halogens, that is fluoride. These kind of orders you try to remember because when questions are there, generally they keep such kind of options. So all these groups are called minus I groups. Based on plus I and minus I, we can discuss some important applications. So the first application is stability. Stability of carbocation. CC I am writing carbocation. Carbocation stability is directly proportional to plus I groups and inversely proportional to minus I groups. That's the meaning. Carbocations means they are in need of electrons. In need of electrons, so you need some electron releasing groups. Plus I groups you can call electron releasing groups, minus I groups electron withdrawing groups. So have a look at these examples. CH3 plus, CH3, CH2 plus, CH3, CH plus CH3. This is a primary one, this is a primary one, but ethyl group, ethyl carbocation. This is isopropyl carbocation, which is a secondary one. Here, this can be supported by this group. Here, this plus charge is supported by these two groups. So, two methyl groups are two plus I groups. So, this is going to be more stable. So, as the number of alkyl groups, that is methyl groups increases, the stability will be increasing. So, carbocation stability, we can take final order, methyl carbocation. When you compare with primary, secondary, tertiary, this will be like this. All this you can explain on the concept of plus I groups. As the number of plus I groups increases, the stability will be increasing. Look at carbon free radicals. Same case, carbon free radicals also, tertiary better than secondary better than primary better than methyl free radical. The meaning is same because free radicals, when you are taking for example CH3 plus, 7 valence electrons we say. When the number of electrons are 7, it is again you can mention this is electron deficient. So electron deficient group means they are in need of electrons. So when they are in need of electrons, stability of carbon free radicals also same concept, directly proportional to plus I groups, inversely proportional to minus I groups. So CH3 dot, if you compare with the CH3 CH2 dot, ethyl free radical, CH3 CH3, the middle carbon is having a free electron. This is isopropyl free radical secondary, this is primary, this is methyl. So the stability order is this is free radical, free radical, free radical. This free radical is more stable if you compare. The tertiary one better than this tertiary will be. So In these two cases, free radicals as well as carbocations directly proportional to plus I groups, inversely proportional to minus I groups. Then have a look at this example. CH2 plus NO2 group is there, CH2 plus is there, and CH3 CH2 plus is there. Here you just see this is a minus I group, this is a plus I group. Here no groups are there. Then the stability, if you see, plus I groups increases the stability. So this is more stable. Here no group is there, CH3 plus you take, sorry. And this is the least stable. Methyl is better than nitro because nitro is minus I groups. So it is going to be decreasing the stability. The same thing you can expect in carbon free radicals also. What happens in carbon free radicals? For the same example, if you consider CH2NO2 and CH3 dot CH3CH2, if you consider, this is going to be least stable. Next to this one, this is going to be highly stable. The reason is this is minus I group and this is going to be plus I group. So plus I groups increases the stability. Now interestingly, when you take carbon ions are electron rich. So carbon ion stability, if you consider, carbon ion stability is directly proportional to minus I groups and inversely proportional to plus I groups. So quite reverse you can say. So tertiary carbon ions, secondary carbon ions, primary carbon ions, and methyl carbon ion, if you take, this will be the stability order. How you can mention this one? I can have a look. CH3 minus, CH3, CH2 minus. Already negative charge is there. And this carbon methyl group is again providing electrons to this one. Because of the negative charge only, this is unstable. And again, it is providing electrons means it is making it more unstable. So we don't require such kind of groups. So plus I groups will decrease the stability. But like previous example, CH2NO2 minus, CH3 minus, CH3 CH2 minus. If you consider this is a minus I group, this is a plus I group, and this is normal methyl group, no plus I, no minus I. If any such kind of groups are there, then the maximum stability given for this one. Because NO2 group is minus I group and minus I group is going to stabilize this one. That you can say by the nature of electron withdrawing. It is electron withdrawing group. So they can ask you some questions like this: CH2 minus. If a fluorine is attached, CH2 minus. A chlorine is attached, CH2 minus. A bromine is attached. Fluorine, chlorine, bromine, all are minus I groups. Minus I groups are good for carbon ions. So which carbon ion makes it more stable? The stronger minus I group. So fluorine is stronger minus I group. So this will be the order. So you need to know the plus I groups and minus I groups order also. At least try to remember few things like NR3 plus is the highest one. Then aldehydes and ketones will type groups will come. After that you will be getting fluorine, chlorine, bromine, iodine. That is mandatory. Along with this, you can discuss about carboxylic acid's acid strength. Strength of carboxylic acids also directly you can discuss here. It is directly proportional to minus I, inversely proportional to plus I. Why? What is the meaning of this? Have a look at this. This is COOH. If it want to be an acid, it should release H plus ion. So COO minus is grouped into form carboxylate ion. So negative charge is already there. So when negative charge is already there, it is in need of minus I groups because minus I groups can stabilize this negative charge. So minus I groups are accepted, plus I groups are not good for the acidic nature of this. We'll have a discussion about this. See HCOOH, CH3COOH, CH3CH2COOH. Here no groups are there. Here one methyl group is there. Here ethyl group is there. And this is the acid part. As we were discussing, this is ready to lose the proton. Then the negative charge will come here. So here minus I groups are accepted. But this is a plus I group. This is even a bigger plus I group. So the acid strength will be like this. So formic acid is a stronger acid than acetic acid, then propionic acid. So more number of plus I groups, less will be the acidic nature. See some interesting examples. This is COOH, 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 COOH. All length is same, but here fluorine is there, here chlorine is there, here bromine is there, here iodine is there. At same distance, four different groups are present: fluorine, chlorine, bromine, and iodine. So fluorine is stronger minus A group, so this will be stronger acid. Fluorine is a stronger acid, stronger minus A group. So when fluorine is present, this will be the more strong acid. So minus A groups, stronger minus A groups are better. Then have a look at this COOH. This is chlorine. COOH. This is chlorine. COOH. This is chlorine. In all the cases, chlorine is only present, and that one chlorine is only present. Same number of chlorines are there, but here it is close to COH group. It is little bit away. It is far from the COH group. So when minus I groups are there, minus I groups increases the stability. So when they are very close, that's much better. So minus I groups must be close. So this is better acid than this. Okay. Next, CH3COOH acetic acid, CH2COOH, one chlorine is attached here, CHCl2COOH, CCl3COOH. If you consider these four, this is acetic acid. Here one minus I group is there, here two minus I groups are there, and here we have three minus I groups. More the number of minus I groups, more will be the stability. So the stability order is again in this way. This is more stronger group. So finally what we can say? If minus I groups are there, they must be more in number, they must be close to COH group, then the stability will be more of that carboxylate ion and they will become good acids. So minus I groups more in number, close in nature, that is, and stronger minus I groups, that is better. If any plus I groups are there, away is better, less plus I groups are better, so they can also better. But plus I groups, if they are present and along with minus I must be stronger, plus I must be weak. So this is one important line. Then basic strength of amines also you can explain. Basic strength of amines. What do you mean by amine? Amines are, for example, if you take this is an amine, RNH2. Nitrogen is having a pair of electrons. Because of the lone pair of electrons, it's a very good Lewis base. It can donate the electron pair. Now you see, this is ammonia. This is RNH2. This is R2NH. And this is R3N. And I am discussing in gas phase, not in solution phase. Gaseous state I am discussing gas phase. Here, nitrogen, if it want to donate the lone pair of electrons in coordinate covalent bonding type, if it wanted to give it, okay, not complete donation, for coordinate covalent bond formation. Here, three hydrogens are attached. These hydrogens do not support nitrogen in any sense. Okay, hydrogens neither plus A nor minus A. But here in this case, if you see, this is called a primary amine. In primary amine, there is an alkyl group which can push electrons towards nitrogen, which is a good support for the nitrogen, because now nitrogen can comfortably give this electron pair for bonding. In this case, there are two nitrogen atoms which can very much easily, two alkyl groups are very much supporting this one. So here nitrogen can donate the electron pair much easily. And here R3, three alkyl groups are there. Some other factors will be there like basic nature, hydrogen bonding and all that affects only in aqueous solution state. Now we are discussing only gaseous state. Remember, this is only gaseous state. So in the gaseous state, what we say is ammonia is a weak base, RNH2 is a strong base. And if you take R2NH, it is much better. R3N is super base in gaseous phase. The reason is here three plus A groups are there. More the number of plus A groups, more the possibility of donation of this electron pair which is present on the nitrogen atom. So these alkyl groups are supporting the nitrogen. They are just saying the nitrogen that comfortably you can give, we are here, like that. So these are the important things about the inductive effects. Next time we'll discuss more about some other effects. So finally what you have to remember is inductive effect is transmitted through sigma bonds only. Inductive effect means the nature of having some more electronegative atoms are creating some induction in the compound, and it may be because of the presence of more electronegative atoms, and it is of two types, plus A and minus A effects. If it is attracting electrons more, that is called electron withdrawing groups. If it is attracting less, they are called electron donating groups, plus A and minus A. So based on that, three factors we can discuss. One is stability of intermediates, and other is strength of acids and strength of bases. For acids, we need minus I groups. For bases, we need plus I groups. Remember, in for bases case, I was saying in only gaseous state. Acids minus I groups are much better. Carbocations and carbon free radicals, plus I groups are better. Carbon ions, negative charged carbon, negative for these, minus I groups are better. Remember this, based on the number, based on the closeness and all that, you have to say the stability. So many questions will be there. Next time we'll discuss about this.